right, here we go.
Alex, you and I
Yo,
have paper.
stop talking. We're getting ready to start class. Start talking. This is what happens when you have to hand out tests and stuff. Okay, we're on page 108 in your science book. What is work? Also have a handout that they've already received. You will have that, a PDF, under your classwork assignment. That is where your questions, your homework questions will come off of the handout, not from the reading, okay? But it covers some of the same information, some of it's not the same. That's why we're doing both, okay? All right, here we go. We will do some experiments a little later on, not today, but as we move forward. Your test will be the 17th. Okay, that's the day before you get out, so you've got to stay focused on this. Okay, you guys will be the 18th, which will, well, maybe not. You might have to do on the 17th also. We'll see. Okay. All right. So we're going to start off. We just want to read in the book here, and then we'll move to the work sheet. Okay. Tell about this morning. You probably woke up, went to school with your backpack of books. Most of you did that. Okay. You lifted your backpack and then carried it with you. If you had a lot of books to bring home, carrying your backpack might have felt like a lot of work. Okay? But in the scientific definition of work, after you lifted the backpack, you did not do any work whatsoever to carry it to the car and then back into the school building, up the steps, and all that. Okay? When you lifted it and put it on, you did work. But after that, carrying it all around, you were not, by the scientific definition, you were not doing work. And we'll try to explain that a little bit. Okay? So the meaning of work, in scientific terms, you do work when you exert a force on an object that causes the object to move some distance. Now, you would think carrying a backpack, you moved it some distance, right? Okay, but there's a catch. Work is done on the object when the object moves in the same direction in which the force is exerted. So if I pick it up, the force is being exerted upward, right? So I'm doing work. Once I put it on my back and I start walking, the force is not upward anymore, it's going horizontally. So therefore, I'm not doing any work. Tell that to your back, right?
Wait, I have a question.
Okay? Yes.
I'm not questioning the test, but didn't you say on the test that Joel was not a form of work? It says that it was standard even the first day of school.
That is how work is measured, dear.
Yeah.
That was not on that. We were not talking about work on the test.
I know.
So then you don't know. You don't have a valid point to stand on.
It said, what is a form that is, it said, what is something that is not a, something that stands for pressure.
Oh, I thought it was just like a standard unit.
Okay.
Okay. I'm
Instead
sorry.
of trying to outsmart the teacher, why don't you just pay attention and try to learn what we're talking about today?
Because the real question is, who has the college degrees and who doesn't?
I'm not saying I don't make. I'm not saying I can't make a mistake. But questioning everything that comes out of my mouth is really getting old, really, really fast. I'm just going to tell you that right now. Okay? I realize in your 11 years you are so wise and worldly. You know, but I can assure you, you've not a clue about most things in life yet. And you shouldn't. You're 11. Okay? All right. So if you pull your books out of your book bag, you do work on the books. If you lift a bag of groceries out of a shopping cart, you do work on a bag of groceries, okay, as you're lifting them up, okay? No work without motion, okay? This is what we talked a little bit earlier when I threw this out. If Spears come up here and pushes against this wall just as hard as he can for 20 minutes, Okay, and I mean, you can see him straining, you can see the muscles bulging out, a whole bit, where he is really pushing hard, okay, and he doesn't let up for 20 minutes. He's done absolutely no work, according to the scientific definition,
It's just no
because that
direction.
wall did not move.
Look, I'm feeling.
He exerted force, but the wall didn't move, so therefore he did not do any work.
Did he move Adam?
What?
And he's like,
He didn't move anything.
Mr. Sizemore,
Yes.
you're doing work when you play video games and you move the controller.
Yeah, you can. That's what I said.
Yeah, I know. And
You're like moving the keyboard. If you're on like a keyboard.
Some of y'all are gonna get your degree in gender studies and not understand why you work at McDonald's. Okay. There are many situations in which you exert force, but don't do any work. Suppose, for example, you are pushing a car that is stuck in the snow, okay? If you've ever helped do that, you feel that you have exerted quite a bit of force, that you're doing some work, right? But if you actually do not get that car from being stuck, if it just stays in that same place, scientifically, the scientific definition says you did not do any work. Okay?
What if you like moved it a millimeter?
That's still doing work.
I mean, does it have to be a certain amount?
It would be very little work. Because your formula for work is force, or work equals force times distance. You move it a millimeter and the car weighs 5,000 pounds, you really didn't do a whole lot of work there. See, that's what I'm talking about. It's not just your typical curious questions. It's trying to buffalo the teacher. Or talking about pigs to your friend because But when you hand the test back, that's when we start worrying about our grade. See, we're starting something new here. You would think they would want to do well, but no, we're not going to pay attention at all for the first few days, and then we'll panic as the test approaches. Okay. Force in the same direction. So why didn't you do any work when you carried your books to school? To do work on an object, the force you exert must be in the same direction as the object's motion. Okay? So that's why when you picked up the book, that force, that upward force, the book comes up, so therefore you're doing work. Okay? When you carry an object at a constant velocity, you exert an upward force to hold that object so that it doesn't fall to the ground. The motion of the object, however, is in a horizontal direction. And since the force is vertical and the motion is horizontal, you don't do any work once you put it in your backpack and start walking off with it. Because horizontal, you're going with the horizon. Vertical means you're up and down. See how that works? How much do you do when you pull a suitcase with wheels? And I love this down at the bottom. It shows you the picture. If you pick it up, you're doing work. But once you start carrying it that certain direction, you're not doing work anymore. Okay? If you get down and you pull it, you leave the whole thing that's on the ground and you kind of drag it along the ground with the two wheels. Now you're doing work because you pull it in the same direction that it is moving. See? If you got it where you got it tilted like most people and you're using the back wheels and you're just pulling it, you're doing some work, but you're not doing, not everything you're doing is not considered work, okay? Because even though part of it is vertical, you're still moving horizontal with it also. So it can get a little confusing if you're not careful, okay? So the only horizontal part of the force does work to move the suitcase, okay? Now, calculating work, okay, we're back again. If Braxton came up here, we had 200-pound barbells up here, okay? And I grabbed one up and I put it above my head, and Braxton grabbed one up and put it above his head. Who do you think did the most work? Nope. It was me. I lifted it further.
Did
we moved the exact same amount of weight, but I lifted it higher, so therefore I did more work.
Yeah, because it's force
You're
times
taller.
distance.
Braxton, you gotta do more work.
Okay? Because it's calculated by distance. Okay? So, when you think about which do you think involves more work? Lifting a 50 Newton potted plant 0.5 meters off the ground onto a table, or lifting a 100 Newton plant onto the same table. Okay? Your common sense may suggest that lifting a heavier object requires more work than lifting a lighter object, and that's true. It is more work to lift a plant onto a table or up to the top story of a building. As you might guess, moving an object a greater distance requires more work than moving the same object a shorter distance. So therefore, although Braxton moved the same amount of weight as I did because I lifted it higher, I did more work than Braxton. Okay? So the amount of work you do depends on both the amount of force you exert and the distance the object moves. The amount of work done on an object can be determined by multiplying force times distance. Okay, that's the formula. Work equals force times distance. It's one of the easiest ones. Okay, you just got to multiply. And it talks about how calculating the work done to move the plant, okay? If the plant was 50 newtons and you moved it 0.5 meters, okay, then you moved it 25 newtons times meters, okay? To lift a heavier plant, you would have to exert a force of 100 newtons, so the amount of work you would do would be 100 newtons times 0.5, or 50 newtons times meters, okay? So when a force is measured in newtons and distance in meters, the standard unit of work in the newton times meter, the N times M, this unit is also called a joule, okay? In honor of James Prescott Joule, a physicist who studied work in the mid-1800s, okay? So 1 joule, or capital J, is the amount of work you do when you exert a force of 1 newton to move an object a distance of 1 meter. Okay? You would have to exert 25 joules of work to lift the lighter plant and 50 joules of work to lift the heavier plant. Okay? Now, you'll take your handout. Okay? Some of it is going to cover the same thing. Some of it throws a new twist to it. Okay? We often use the word work in our everyday lives. For example, we would say that getting good grades in school takes a lot of work. Okay? In physics, the term work has a specific meaning. Work in physics occurs when a force acts on an object to move it some distance from the start point. This is also called displacement. Okay? When you move something from point A to point B, that is considered a displacement. Work is calculated as the force times the distance. So the equation is simply work equals force times distance. Okay? How you measure work, the standard unit for work is a joule. It's the same as a newton times meter, where the newton is the force and the meter is the distance. Okay? So they are the same thing. Force and displacement, the distance or displacement in work, and the distance from the start point to the end point, the amount of traveling in between doesn't matter. Okay? For example, if you lift a weight off the ground and then place it back on the ground, the distance or the displacement was actually 0. Okay? So if you lift something up, you put it back down, you didn't displace it actually, so the work was 0, or displacement is 0, okay? Measuring work can sometimes be tricky in order for the equation W equal FD, for force times distance, to work. The force used in the equation must be the force used to cause the displacement or the distance. Also, remember, for work to have occurred, the object must be displaced by force. Okay? Otherwise, the distance, or D, in the formula is 0, and the work would be 0. So that we're back again to pushing against the wall. Okay? I mean, we all know in all reality, I mean, you can actually get a pretty decent little workout. You can strain your muscles up here pushing against that wall hard enough. You know, if you pump your legs and the whole bit, I mean, you're actually, you know, your body thinks you're doing some work. Okay? And in all reality, you are. But by the scientific definition, because that wall did not move, you didn't do any work. Okay? It's kind of the same way with lifting weights on a machine. Okay? You go and get on a shoulder press machine and you're lifting 100 pounds up and down, you're doing some work. But when you finish, since those weights were not displaced, actually, there was actually no distance there. They were not displaced. Scientifically, you might not have done any work. Okay? Your body knows you did, but scientifically. So again, remember that. Okay? Okay? We're talking the scientific definition here. Okay? So don't be tricked. Measuring work can sometimes be tricky. In order for the we just did that. I'm sorry. Some examples. Someone pushing on a wall with all their might, but the wall doesn't move. No work has occurred. Okay, this is because the distance is 0. If someone is using force, not like this one. If someone is using force to hold a rock over their head while walking eastward across the field, no work has occurred. Why not?
Because the force is not.
Yeah, because they did work when they lifted the rock, right? They did work there because the rock was going in the same direction as the force. But when they started walking, the force is going this way. I mean, the force is up, but it's moving this way. So therefore, no work is being done. Now, if you let go of that and hit Chef in the head, you're going to pretty
But if
you're going to think that you did some work.
lifting this up, would that be?
You actually do work there. Yeah. Yes, sir.
Good
All right, stop, please. I got a question from Kayla. Yes.
So I want to clear about something. So if you pull something up, but then you put it back down, so you don't do work if you put it back
You
down.
did not move it any distance, is what it's saying. You did work when you lifted it, but when you put it back down, there was no displacement of it. So technically, because it was not displaced, you didn't do any work.
Wait, so what about what about a brake on a car? When you put, is that where when you're driving? Because the car drives, not
Yeah,
you.
technically.
Or because the machine is making it run, but you pushing the pedal is pushing the pedal work or something?
No, not really. You're applying force, but again, you're not, yeah.
So wait, if you do like 10,000 push-ups, you don't do any work.
You don't do any work because there was no,
Great job,
in fact, that's one of the things we want to talk about. If you do a full push-up, okay, and trust me, from somebody who spent a lot of times in the military and have done probably well over 1 billion push-ups, if you do a full push-up, lifting yourself up and then back down, the total work is 0. Because the total distance from the start point to the end point is 0. Even though you pushed up, when you come back down, you didn't displace it. Okay, there was no displacement. Okay? There was no displacement. Same thing. Okay?
If you throw a barbell, then
If you, but here, listen to this though. If you drop your pencil, then work has occurred. If you do 100 push-ups, you didn't do any work, but if you drop your pencil, work occurred. This is because displacement of the pencil from your hand to the ground is greater than 0, and in the same direction as the force acting on the pencil, which of course is gravity.
So if we're doing our fitness test and we're all doing push-ups and your size was like this.
If I dropped my pencil, I did more work than you did doing all those push-ups. scientifically speaking.
Now, like.
Now, if I was doing the push-ups, I would argue the point that I was doing more work than you. Okay? All right. A baseball player throws a ball with a force of 10 newtons, and the ball travels 20 meters. So what is the total work that he did? Okay? Nobody knows. 10 times 20, guys. 200 joules. Okay? 10 newtons times 20 meters. All right. Now, you can see the more complicated problems here. You will not have any questions on that. You will not have, not on your homework and not on your test.
This one's fairly easy.
Okay, that is, that's a little bit more advanced than 6th grade introductory to rudimentary physics, okay? All right, some of your questions might come from the interesting facts about work, so you might need to, want to look over those. Because it talks about another unit of work is the foot-pound. And 1 foot-pound is equal to 1.3558179 joules. Okay? It's kind of like when we get into power tomorrow, a horsepower. You know why it's called horsepower?
Yes, because that's how much a horse would.
Because it's how much power, a horse has. So if you have a car that has 400 horsepower engine, it would be the equivalent of 400 horses pulling the car.
Well, it depends on the type of horse.
All right. Thank you.